Now you can see this one here, your assignment number 2. A rectangular reinforced concrete beam is simply supported on two masonry walls, 230 mm thick, and clear span is 6 meter. Live load, that is imposed load on the beam, is 15. It is service load, means you have to, it is not a factored load, it has to be multiplied by 1.5. So whenever service load is given, you should be careful. It is not a factored load, 1.5 has to be multiplied. Design the beam, assume the width of beam is given as 250. Use M20 and FE, check for shear and deflection. So check means you have to design for shear as well as check for the deflection. That is KC, KT and KF, L by B basic. That deflection formula you have to use here. Second one you can see. This is the one already it has been solved. Means span may be different and all. Second one is you can see this. You try to do from today onwards, you will come across some difficulties. See, while doing assignment, if you do it on your own, you are going to get, you will get some difficulties you will come across. That time we can discuss. Otherwise, if you just copy from somebody and write it, it is not going to help you much. So on your own, you should try in the exam, whatever you try, design a rectangular beam of 230 by 600. You can note here dimension is given over an effective span of 5 meter. Superimposed load on the beam is 50 kN. Now you see this 50 kN. Here it is 1.5. Span is more, load is less. Here span is less, that is 5 meter. Load is more. So it is a likely candidate for doubly reinforced beam. You can see here, dimensions you cannot change once it is given. Now here, right now you don't know whether it is a singly reinforced or doubly reinforced beam when you read the problem. When you start solving it, what will happen is you will find that MU limit is less than MU because of heavy load. Load is more. 50 kN is here, 1.5 is here. You can see. So comparatively, load is heavy, span is less, and dimensions are already fixed, 230 by 600. So this is the most likely candidate for doubly reinforced beams. So take effective cover as 50 mm. Now, since effective core is not clear about whether it is for tension steel or compression steel, you can adjust accordingly. If you want to make it the ratio d dash by d, if you don't want to interpolate and or go for higher value, that time what you can do in double reinforced section, you assume a suitable cover so that the ratio d dash by d becomes 0.1 and directly use the table F and find out FSC value. So just check this one because it is when you read the problem, don't be under the impression that the problem will be always singly reinforced. But if the dimensions are not given and it is your choice, that time what you can say, I will change the dimensions and I will still design one way, that is singly reinforced beam only. It means if MU limit is less than MU, okay, what I will do, I will try to increase the MU limit. How it is? 0.138 FCK BD square or whatever it is. B and D, if I increase automatically, MU limit will be more. It means, but here there is no choice to do that. Dimensions are given. Okay, since dimensions are given, here they are not telling you to use a suitable dimension. You have to design a doubly reinforced beam. Here also you can see, even a cantilever beam, 4 meter span carries a load of 40 kN, relatively high load it is. The width of the beam is fixed. Design the beam for flexure shear. Now here what will happen is if you try to design a singly reinforced cantilever beam, what will happen is the depth will be too high. Just try this one because again you may have to design this as doubly reinforced cantilever beam. Only thing that you should understand is MU is WL square by 2, not WL square by 8. This is what you need to understand here. M20 and FE415 is given. You have to be good in both M20 FE500 or M20 FE415. Most likely is FE 500 only from this question paper, I think. For 18 series, they may prefer FE 500 only. So you have to be good in both. Huh? Constants will change. So the constants are changing, which are those constant. If instead of FE 415, FE 500 is used. You have to be careful about that. That is why I'm telling you, on your own, you try to solve these problems. In case of difficulty only, you start asking here and there. If you copy paste it, it is of no use. So this is third example is, I think it is again doubly reinforced section. So next observe this. So you have to sit today only in 3-4 days you will be able to solve these problems. Design one of the intermediate T-beams for a hall measuring 7 meter by 12 meter. Beam are spaced at 3 meters center to center. Depth of slab is 120. Live load on slab is 9.5. Including the floor finish, everything is added here. So M20 and HYSD bars. HYSD bars, it can be FE415 or FE500, but choose FE415 and try to solve it. There will be initial confusions will be there in all these problems. Unless you try on your own and commit some mistakes in the beginning, you are not going to get anywhere near this subject. So you should try and commit some mistakes. Otherwise, there is no other way of understanding. Question number 5, you can see a rectangular RCC beam 300 by 700 with an effective core of is subjected to the following. Factored BM is given, factored shear, factored torsion is given. Design the beam for flexure and shear using M20, and whatever I have solved, only these values are different. You can go back to that video that is uploaded, wherever 191, the values are different. Open those videos, T-beam video is there, you open that one, design T-beam. Open the video lecture of whatever I have done in doubly reinforced beam, open that one. Once again go through that one. Try to take others help minimum. Depend on others for very minimum percentage, I can say. Because in the examination, you will be all your own. So like that, you try these problems. If there is any problem, you can directly call me, or initially you try this one, or you can call me whatever is the difficulty you are facing. But on your own, you try first. So last date is given as 17/11. So still 7 days are there. Daily one problem also if you solve, you can easily complete it. And it is not difficult to solve one problem in a day. So let us go to the next slab
Sir,
designs. Anybody has any question here?
sir, flexural strength ಹೆಂಗ್ ಕಂಡುಹಿಡಿಯೋದು sir?
Flexural strength of what?
Flexural and shear ಐತ್ರಲ್ಲ sir, ಅದ್ ಹೆಂಗ್ ಕಂಡುಹಿಡಿಯೋದು sir? Flexural.
Flexural means that is bending only. Flexure and bending are same.
Okay.
Okay, if any other thing is there, you call me later, because I will complete this slab design. You call me after 3 o'clock. I will tell you what it is. Flexure and bending are same. Okay. Just try first. See, don't get confused. Try to solve these problems one by one on your own. Try on your own where you are getting stuck. You check it where exactly you are getting stuck when you are on your own. Because the person who has solved the problem and is given the PDF to you, wherever he got stuck is different, and wherever you are going to get stuck will be different. That is not going to help you here. That is why you try on your own first. Exactly where you are getting stuck, you should come to know. That is how you should diagnose. Let us go to this next one here. Observe. That is, the steps I have already explained, but anyway, I'll repeat it. Observe here. Usually, initially, let us start with types of slabs: one way, two way, and continuous. Continuous is if the supports are more than two. More than two supports are there. If the slab is supported on more than two supports, it is a continuous slab. Two-way slab, one-way slab. One-way means steel runs only in the main steel. In the other direction, whatever we call it as distribution steel runs. What is the purpose of that? I'll tell you. Next is steps in the design of one-way slab. First, check for the type of the slab. Whether it is one-way or two-way, you should check. Simple method is Ly by Lx. Ly by Lx should be more than 2. Okay, then it becomes one-way slab. It means that predominantly it bends in only one direction. So here observe this one. Once again, I am repeating this. I'll show you two rooms, plan of two rooms, which is likely candidate for two-way slab and one-way slab. We should look at the diagram only, you should tell. See, this one of the dimension is more than 2 times. So this is the likely candidate for one-way slab. Which one? This one. And steel runs like this. Main steel runs like this on these two supports. Span will be like this. Span is this one, horizontal. That is, this will be the span, L or L effective, whatever. This is the span. So if you look at the plan, you should be able to understand which is whether it is one-way slab or two-way slab going to be. Now you look at the other diagram. It is a likely candidate for two-way slab because it is almost squarish. The bending here, the bending takes place only like this. It bends only in this way because these are the two supports. There are all 4 supports are there in two-way slab. Not only it bends like this, if you look from this side, if you look from this side, this bends just like a saucer, cup and saucer. Saucer you have seen, cup and saucers. It becomes like something like a saucer, a two-way, that is two-way slab becomes a saucer. It is not like this. It is only it bends in one direction. Between the supports it bends. There are 4 supports are there in two-way slab. It bends like this also, like this also. The deflection will not be same, but you have to assume that they are same. So it means the reinforcement, main reinforcement runs like this as well as like this. It means in both the directions, main reinforcement is running. Now what will happen in this case? In this case, all these steel which are running like this, these are distribution steels. Just to reduce the effect of shrinkage and all, distribution steel provision is just for practical considerations. There is a shrinkage and creep of concrete. To control that one, this distribution steel is provided. I'll show you while solving the problem how to calculate it. Now observe, calculate the total factored load. Check for the type of the slab and fix the trial depth. Maybe slab by 20, something like that. One empirical formula will be there. Use that span by depth, whatever that ratio. Based on that, you arrive at the depth of the slab. Depth means it can be, as I told you, 100 to 150 mm. In this range only the slab thickness will be there. So calculate the total factored load and effective span. Once you calculate the dimensions of the slab, dead load can be calculated. Dead load or self load can be calculated. Live load will be given. In that way, you can find the total load and effective span. Again, the formula is center to center distance between the bearings. The way whatever beam effective span was calculated, same thing. So what happens here is effective span is the smaller of center to center distance between the bearings or clear span plus effective depth, whichever is smaller out of these two, same as beams. Next one is determine factored bending moment, factored shear force, and check for the depth provided. So how do you check whether the depth, let us say I have assumed 120 mm thickness of the slab. Now I should check whether it is sufficient or not, whether I should go and revise the design. Whether the depth is insufficient, you can check it here, then only go for steel calculations. If the depth is insufficient, you should not go to the next step for calculation of reinforcement. So here how to get it is, once you find out WL square by 8 and WL by 2, that is bending moment and shear force, you have to find out MU limit. Okay, once you find mu limit, it has to be more than factored bending moment in case of slabs. If it is not there, you have to increase the depth and revise the design. That is the only option left. You cannot say I will design to doubly reinforced slab. Such things are not there. Okay, because it is a very thin member. 150 is a very comparing to 230 or 500 thick beams. As you have seen in the problems, 500, 550, 600, 450, different depths we have seen. But whereas slab is just one fourth of that, just hardly it is 100 and slight increase in the depth makes it mu limit more than mu. Reinforcement steel main and distribution. Check for deflection. Check for development length is last step, which is not written here. Check for development length. That is there in the, this one, but it is optional actually, as I told you in the previous class. In the examination, if time is there, you go for sixth step. Otherwise, this much is enough. In every question paper, they say check for deflection. They don't say check for development length. But complete design means check for development length has to be carried out. So only this page is little bit blurred. All the remaining pages are okay. Let us say some blur it has come suddenly. One-way slab I'm going to design. So don't try to read it. Just listen what I'm telling. Only this page is little bit blur actually. Next page and all are very clear actually. See this. All dimensions, everything is clear. So here, try to understand what I'm actually telling here rather than trying to read it. The room dimension is 9 meter by 3 meter. It means the dimensions are given like this. This is 3 meter by inside dimensions they have given. This is 3 meter inside. This is 9 meter. Dimensions are given like this. Load on the slab is 3.5. You cannot read it, but it is there in the next page 3.5. And floor finish is 1 kN per meter square. See, when you provide this granite or vitrified tiles or whatever, so a lot of choice is available for us. Or pota stones, pota tiles, lot of different tiles are there. Roughly per meter square, the weight of the tiles is taken as 1 kilonewton. So over the slab, tiles have to be fixed. So that load is also given. Floor finish it is called as. Design the slab using M20 and Fe415 steel. Assume the thickness as 230. Thickness of supported is not slab. Thickness of the supports. Now check for the type of the slab. Ly by Lx is 9 by 3, which is more than 2. Ly by Lx is 9 by 3, more than 2. That is why the slab is designed as one-way slab, because the ratio is more than 2. Now start with a trial depth. Empirical formula is there. Let's see, a lot of different expressions are used in different books to start with a trial depth. So what I have done here is, instead of going for complicated equations, I started with the span by 20. Span by 20 is taken here. Slightly I have increased it actually, but anyway, span by 20. Span is 3000. So this 9 meter, whatever I have shown here, this 9 meter is not used anywhere now. Only for checking Ly by Lx, whether it is more than 2 or less than or equal to 2 or whatever. So only for that purpose 9 meter is used. In no calculations it will come now. Only 3 will come, 3 or effective span. Since I don't know the effective span right now, I'll go with clear span by 20. So span is always the smaller of the dimensions because steel runs along this direction, main steel. So 3000 by 20, 150. So what I did from here was, even though small d is 150, I'm trying with a capital D as 150. Again, this is all empirical, I'm telling. If somebody tries 100 and designs it and checks are okay, as I told you, design will not be unique. Design is not unique. It can have more than one solutions. So let us try D is equal to 125, capital D is 150. Based on this empirical equation, I am trying for this as a first trial, I can say. As a first trial, I am going to start with these two dimensions, 125 and 150, small d and capital D. Next, now total factor load and defective span. As I told you, step 2 is factor load. Observe this. Dead load. How dead load is calculated? It is dead load is, you can see this thickness. I think it is not clearly visible, but just listen to me. The dimensions of dead load means density into volume. So you observe this one. Thickness is 150, so 0.15 into 1 into 1 into 25, 3.75. So once again I repeat this one. Dead load is density into volume. So volume is how much? Density, you know, it is 25. Volume is 1 meter into 1 meter into thickness is 0.15. 150 mm is 0.15. So 1 into 1 into 0.15 into 25 is the density. Like that it is taken. So 3.75 live load is given. Floor finish is also given. So add all the three: dead load, live load, and floor finish. Total service load is 7.7. So this is service load, total service load. Therefore, factored load 1.1, 1.5 times service load. So it is subjected to 11.625. The load on the slab is 11.62. It includes dead load, live load, and floor finish, and it is factored. 1.5 is multiplied. So this is the load calculation. This page is not blur, it is clear now. So effective span is, now you can see these dimensions. 0.23 it is given in the problem. 230 mm is the support thickness. Maybe it is a column or a load bearing wall it is. You can assume anything here. Now 0.23 thickness is that inside dimensions are given as 9 meter by 3 meter. From this one I should get effective span. So effective span is smaller of clear span plus effective depth. So 3 plus 0.125 because small d is 125 mm. So that is 0.125 meter. So I'm getting 3.125 or center to center distance between bearings. One more way of calculating effective span is this. So this is center of this, center of this. This is one more way of calculating effective span. So inside is 3 meter. This side 0.235 by 2. This side 0.235 means 0.23 by 2. Again total is 0.23. So 3 plus 0.23. So it is written here. We can see 3.2. So 3.23 and 3.125. Smaller is 3.125. That will be taken as effective span. So I got the effective span as 3.125. Now I am going to draw this diagram like this. LE is taken as 3.125. Support thickness is 0.23 given in the problem. Next is step 3. Factored shear force, bending moment, and check for the depth also. So now after finding this one, I'm going to use effective span here 3.125. Load is calculated already 11.625. Draw the bending moment shear force diagrams. That is mu is equal to WL square by 8. Vu is equal to WL by 2. Effective spans are considered. So 14.191, nearly I can say 14.2 into 10 raised to 6. This is 18.16 into 10 raised to 3. I can see 18.2 into 10 raised to 3 Newton. So SFD and BMD are drawn with the maximum values of BM and SF. These are all factored values. So next is Now you have to check for the depth, whether the depth of 125 and 150, are they sufficient or no? For this one, MU limit you calculated, MU limit 0.138 FCK square, or if there is a confusion, open this page number 96, write the formula like this. Depending upon whether it is 500 or 415, constant 0.138 will change. You have to be careful about this. For example, if E500 is there, this value is 0.133. Just check that one. That is why you should not go wrong for wrong substitution of constants. Constants, they depend on grade of steel and concrete. So here 0.138 and all is done. Now I am getting a value which is 43.125 kilonewton meter, which is 43.125 into 10 raised to 6 Newton mm. If you converted it into Newton mm, multiply by 10 raised to 6. Now let us check this one with mu. It is simply, see, simply it is 14. So the value is much more higher. So it is comparing the value with factored moment, we find that mu limit is more than mu. Hence the depth is adequate. Whatever depth, I can reduce also in the second cycle. But in the examination, you cannot do all that. You cannot go on solving the same problem again and again and again. So what, even if it is uneconomical, in the examination, if the solution is uneconomical, there is no problem. In real life, it has to be economical. To make it economical in real life, you have to redesign 2-3 times and optimize it. Then you say that this is the final design. You can do that. If you do like this, it will be economical. But in the examination, economy should not be considered. Otherwise, you'll be wasting a lot of time there. So comparing the value with factored moment, we find that mu limit is more than mu. So that the depth is adequate and section is under reinforced. Next step is, now what I have done, I have calculated mu limit, compared with mu, everything is okay. Now I should start reinforcement. So reinforcement consists of main reinforcement and distribution steel. Means in both the directions I have to provide the steel, but in one direction it is called as main steel, in the other direction it is called as distribution steel. Again, I'm going to use the same formula here. AST is equal to 0.5 FCK BD by FY 1 minus all this. So you try to avoid these equations in the examination if you know how to use SP16. See how to calculate all this. So this is not going to take a small time here in the exam. We can try this. See, if you are practicing this formula regularly using calculator, automatically you will come down on the time that is taken. But if you are not practicing this formula in your house, in the examination, it is going to take maximum time. So if you cannot see, if you want to see, if you want to use this formula, how fast you are getting, how fast you are able to get 334, how fast you are getting it using this formula, that is going to matter much in the examination. So next is a one more is whatever is given on page number 96 IS 456, this formula, second formula I'm giving. Don't use all three in the exam. I'm just giving you in this problem what are the options available for you to find out AST. So mu is, if you forget this formula here, because this formula is not there in the code book, if you forget it, only option is quadratic equation. Go to page number 96, IS 456-200. This formula is there. Substitute all the relevant values. In mu, don't use mu limit value. Wherever mu is there, you should use bending moment value, factored bending moment value. Only for checking purpose, mu limit was used. Now AST is 333. Here it is 334. I'm getting. All are same actually. Close values you will get. Values will not be same, but they are very close. Next, PT, one more formula I have introduced here. PT is equal to 0.5 FCK by FI. Directly PT I am getting. After that, PT is equal to AST by BD into 100. From this one, you get AST. First find PT, then go to this formula here. Whatever I have written, I think you are able to see this one. You already know this. Just observe this. That is, from here, find out PT, substitute PT here, find AST. This is also as good as it is as good as it is. It is a little bit easier than the first formula. This one, little bit, it is less time consuming, but still it is almost same formula. It is. So if you use any three method, fourth method is the best one. That is use table SP16 table 2. Fastest of all these, because you see in the notes what I have done in the examination, don't try to practice all this, because see I have calculated AST using already three methods I have used. You are supposed to use any one method to get 334 or 335 or whatever. Don't use all three methods. It is again a waste of time. Now what I will do is I will suggest don't use any of the three. Go with table 2 of SP60. That will take hardly 2 to 3 minutes to find AST. But in the very rare case, if that SP book is not allowed, that is not going to happen. But even then, in the worst case, at least any one of these formula you try to remember. And in one more case, if you forget everything, how to calculate AST, go to page number 96, substitute everything in this. It becomes a quadratic equation in AST. Find AST from that. Best is, as I told you, in order to attempt all questions, SP16 is the best. So you have to decide that. So if you want AST, here I have not used AST and it is SP16 and calculated here, but just now I have done it. If that page is already loaded, then I will be able to explain. It is not getting loaded, I think. I have done it just now. I calculated by that method also using SP16 table and all. I'll show you that one. Okay, I'll just do like this. I'll open this page. Observe here. As you can see, this takes hardly 2 minutes to get AST 334. AST 334. You can see here. This is old problem. Here, mu by BD square you have to calculate. Mu by BD square. It is working out to be 0.908. I don't know whether if you can calculate it, check it. Use mu by BD square. Mu is a 14.191 into 10 raised to 6. Mu. Anyway, I'll show you again. Just observe this, how it is SP16 table is used here. One more method, fourth method. Okay, these are the three methods that I have discussed here. Okay, see this. Now I'm trying to explain the fastest method. Fastest method is find out mu by BD square. Mu by BD square. It is 14.191, or you can say 14.2 into 10 raised to 6 divided by BD square. So B is always 1000 in case of beam slabs. Slab is an imaginary beam with B 1000, thickness 150. B is more, D is less in case of slabs. So how you understand this one is, it is an imaginary beam only with a width of 1000 mm. 1 meter is the width of the slab. So the cross section of the beam, a slab to be considered is 1000 by 125. I'll show you this diagram here. Imaginary beam only like this. B is 1000. That's 1 meter. This is capital D or small d, whichever is required in the design. Usually small d is taken, which is 1, 2, 5. Now observe this one. I'm going to find out mu by BD square. So mu is 14.2 into nearly 10 raised to 6. I'll substitute in mu. BD square, B is 1000 for slabs. B is 1000. D square is 125 raised to 2. If I do like this, I checked it here, I am getting 0.908. What is that? Mu by BD square. See this one. First column is mu by BD square. So I have to calculate this one first. So mu by BD square, I am getting it as 0.908. 0.908. I'm going to take it as to avoid interpolation. See, if the value is very close to any of these numbers, you don't have to interpolate. If it is exactly in between these two numbers, that time it is necessary to interpolate. Okay, so what I have done here is, again, I try to save time for interpolation also, but you have to be very much careful here. I got a value mu by BD square 0.908. I have to interpolate these two numbers now, or I have to consider that number and proceed. For example, see this. 0.9 is here, 0.95 is here. My value is mu by BD square of this problem is 0.908. I have two options now. 0.908 I will interpolate and get a value which is in between, corresponding to 4. See, this is 415 is here. See, this is 415 line. This line is 415 line. So what I will do here is, I have two choices here. 0.908, directly I will take it as 0.90 and I'll use 0.264 and complete the solution. One choice. Second is, I'll use these four numbers, that is 0.9, 0.264, 0.95, 0.280. I'll use these four numbers and interpolate it. For 0.908, how much will be 80 PT value? These are PT values. 0.264 and 0.280 are PT values. Now what will happen if I interpolate, because the mu by BT square is 0.908, which is more than this, less than this. The value of PT will be in between 0.264 and 0.280. So I have to do like this. Otherwise, I'll take a risk. What I will do? Again, I'll try to save the time. I'll take it as 0.908 is very close to 0.90 only. Then I'll directly use 0.264. Okay, so 0.264, after using it, this is the value of PT. It is equated to AST by BD into 100. It means 0.264 equal to AST by BD. B is 1000, D is 125, small d, into 100. So AST is to be calculated. From that one, I calculated AST, I got the value as 330. I got the value as 330. I'll just try to, if at all it is available, that page I have already taken. I don't know why it is. So now you can see this one here. So AST is calculated now by 3-4 methods, but in the exam only one method has to be followed. Now you can see this one here. So this is calculated like this by different methods. Once this is calculated, you should check. Actually, I have check for minimum reinforcement here. Now this formula, whatever minimum steel has to be there in the slabs, that formula I should use. So I am going to use 0.12% of gross area. So again, it is a new term now for you for slabs. This is new term. So after finding 334 or whatever AST by any one of the methods, okay, you should not directly calculate the spacing and diameter. Check it with this value, 0.12% of gross area. So you see this 0.12 by 100 into 1000, B into capital D here. Gross area is gross area of the slab, which is B into capital D. So 1000 into 150, capital D it is. So 0.12%, 0.12 by 100. So it is giving us a value which is 180. Now compare 180 with whatever value you have calculated, that is 334 or something like that. So out of these two, the higher value should be selected. Sometimes in case of a footing design, 0.12% of gross area will be more than whatever AST we have calculated using bending moment value. Using MU, whatever we calculate, in case of footings it is happening, that value will be less than this 0.12%. So whichever is more, you should choose out of that. Now once you calculate, now this is 180 is less, I am going to use AST as this kept. AST will be that one only. Now you can see here, decide the diameter of the bars. Usually it is 8 to 10, 6, 8 or 10, preferably for this type of we can say residential and all, it is 10 to 12 bars are used. Maximum is 10 bars are used. 8 and 10 bars are used for slabs. So I have to choose the diameter now. Spacing of 10 bars. So spacing is calculated like this. It is 1000, which is width of the slab, into AST, area of one bar. Area of one bar divided by total area. So directly we'll get spacing like this. Spacing of the bars in the slab. So S is equal to width of the slab, which is 1000, AST, area of one bar of 10 diameter, divided by capital AST. Total area calculated from either SP16 or any one formula, because that value is higher than 180. So higher value, that is 334, let us say, that is kept here. 234 we are getting. Again, directly you cannot use 230. Again, it has to be checked against this condition. The condition is spacing should be smaller of whatever I have calculated here. First one is this one, smaller of this, that is written here, smaller of 3 times the depth, 3 into 125, or it should not be more than 300 in any case. So out of these three possible spacing values, choose the smallest one. Therefore, provide 10 at 230. Out of these three, you can see the smallest is 230. So what I will do here, after checking for this condition, so I'm going to provide 10 main bars at 230 center to center. Now diameter check. This is on page number 48. So this condition, if you forget it, this condition, whatever is there, it is on page number 48 only. This condition, spacing should not be more than this, these possibilities. Next is check for the maximum diameter, 150 d by 8. This is the formula. So 18.75 maximum diameter. It means you should not use any steel rods which is more than 18 diameter. No, that is the condition it gives here. But anyway, you are using 10 rods. Or phi should be less than d by 8. It means diameter chosen should be less than 150 by 8. 150 is capital D. So both conditions should be satisfied. It may otherwise whatever diameter you have used, it will be wrong. 10 satisfies both of these. So there is no problem. So AST actually provided is this. Actual AST provided is 341. How I calculated this, observe here. Actual AST for slabs. First I have written the width B, that is 1000. 5 by 4 into 10 square, 1 bar divided by 230. What is this 230? It is spacing. That is reverse of this formula. Where is that? See, after choosing, finally after choosing the diameter and final spacing, you should calculate what is the actual value of AST you are getting now. That is important here. Just observe this one here. Look at this formula here. Now after finding, let us say I am having a spacing, I have finalized 230, diameter I have finalized as 10 Now I'll substitute here spacing 230, then pi by 4 10 square I'll substitute, then I'll find AST. AST I should get. That will be the actual AST provided. That is how I have calculated here. See. Okay. It is here. See. So actual AST is equal to 341. So how I got this one is 1000 pi by 4 into 10 square divided by the spacing. Reverse of this formula. Reverse of this formula. In that way, I found out AST value, capital AST value. Okay. Is it clear this one? Now the distribution steel is 0.12% of gross area. So 180 mm distribution steel, the steel which runs perpendicular to the direction of main steel. So it is also very simple here, 0.12 into gross area, 180. Already we checked it once. So 180, spacing of 8 mm bars. I am going to use distribution as 8 mm bars. So 1000 into AST by total AST for distribution steel, 279. Say, let us say 270 I am writing here. Again, it is should be the smallest of 275 times D here. For distribution steel, it is 5D. For main steel, how much it is? 3D. So 5D is accepted, or 450 mm. In any case, it should not be more than 450 mm. Out of these three, smallest is 270. So this is how you can design it. I'll stop it now another 2 minutes and just show the diagram, rough diagram, and I'll stop it. So this is your line of the slab. Main reinforcement is, let us say, this is main reinforcement. See, detailed diagram I'll show you later on. That is again half an hour discussion is there for that. With diagrams you have to see that how to bend. These are alternate bent up bars actually. I am not showing it here. These are, what are these bars? These are distribution steel. It means these are 8 mm at 270 center to center or distribution bars. What about 10 mm bar spacing? 230. 10 mm at 230 center to center. So these red color bars are main bars, which are 10 mm at 230. Blue color are 8 mm bars at 270 center to center. This is your design is completed, but the detailing is one more part. It is how to bend the bars, at what distance I should bend. Alternate bars are bent up.